Hi, welcome back to another discussion of anemometers. And actually, we're working our way into wind direction, which is wind vanes. So, we're going to look at the dynamic response of a wind vane, how a wind vane will respond to a change in wind direction. So, this is what we're looking at, a step change. And we can describe that mathematically rather easily, although it is complex. If you look at other changes such as a ramp change or a sinusoidal change in the wind, it gets much more complex. So we're going to stick with the simplest, which is a step change in the wind. What do I mean by step change is that initially it's coming from one direction. Instantaneously the wind changes to another direction. So, what's going to affect the wind vane? What are the forces that are driving it to turn into the wind? Well, one of them is torque. Torque is a force that's applied over some distance, and it's a rotational force. So that torque force results from aerodynamics, and also it depends upon the distance from the aerodynamic center of the airfoil to the rotational center, in other words, the shaft center of the wind vane. Also, it depends upon the inertia of the wind vane, and that has to do a lot with mass and other factors. And then finally, of course, probably the most obvious is how strong is the wind. So let's break this down a little bit. We got to do some math, so we have to start defining some variables. And we're going to define, or we're going to call theta v the direction that the wind vane is pointing. And then theta itself is the direction that the wind is coming from. So it instantaneously, the wind changes from theta v to theta, and the wind vane does not change instantaneously. It takes some time for it to swing over to its new direction, theta. Of course, v is the wind speed, and then r is the distance from the aerodynamic center out to the pivot point being the place where the wind vane rotates about, in other words, the shaft. So what we're looking at here is the wind vane moving or accelerating. It's going to be accelerating from a direction theta v to direction theta. So that's a change in theta. That's delta theta over some period of time. But it's not just moving at a steady rate. It's actually accelerating in that direction. So that would be the change with time of the change in the angular speed, the change in theta with time. And so that's our left-hand side of the equation. So it's the acceleration, the angular acceleration of the wind vane. And what causes that angular acceleration? Well, a few things. We already talked about the aerodynamic lift that's generated by that airfoil on the wind vane. So that's L, that's your aerodynamic force. R is the distance from the center of the pivot point out to the aerodynamic center. And then I is the inertia of the wind vane. And as I said, factors such as mass and also bearing friction and other things affect the inertia. As you remember from your basic physics, inertia is the ability for an object to stay where it is. It has to move, or it has to be forced to move. So what are the things that are causing it to stay pointed in one direction? So we're going to break the aerodynamic force down. If you had a course in aerodynamics, or even for that matter, if you've been in a private pilot course or commercial pilot course, you'll be familiar with this equation. Lift is equal to the area of the airfoil, the coefficient of lift, the density of the air, and then the velocity squared. And what we're missing there is a 1/2. So it's 1/2 of all this. That's your basic lift equation. That's the lift force that's being generated by the airfoil. And the coefficient of lift depends upon the angle between the airfoil and the wind. So this angle is typically called, in aviation, we call it the angle of attack. Here we're just going to denote it as theta minus theta v. It's an angle between the wind and the direction that the airfoil is pointing, or the chord of the airfoil. And then multiply that by some constant alpha, and that gives you the coefficient of lift. And it varies with this change in angle. As the angle increases, the coefficient of lift increases. That just makes sense. So this is our equation. We're going to stick that coefficient of lift into our lift equation. And as you can see in the bottom, this is our new lift equation. So we're going to stick that into the equation we have for the angular acceleration of the wind vane. Things start to get a little bit messy. We haven't really broken down the inertia of the wind vane. We haven't stuck anything in there yet. And we're just going to leave it as is. We're not really going to define that. To make this equation look a lot simpler, we're going to call all that stuff t squared. So we've got t squared now, and what we have is a differential equation. Actually, it's a second order differential equation that is non-homogeneous, or that is homogeneous, because we have a change in theta. So the solution to that, believe it or not, is a sine or cosine wave. It's a trigonometric function, and it looks kind of complicated. But basically, what this says is the direction of the vane at any particular time depends upon the direction of the wind, and also all these other factors, the coefficient of lift and things like that we included in the t. So at any particular time, we could figure out the direction the wind vane is pointing based on these factors. So what this says is that the wind vane will oscillate as a wave about a given point, around the true direction of the wind. It's going to oscillate back and forth, and the oscillations are going to have a certain amplitude, and they will not change with time. We call this an undamped solution, and it looks like this. So the dotted line represents the instantaneous change in wind direction, as you can see. So the wind vane starts out and starts to correct itself towards the true wind direction, theta, overshoots it, and then oscillates back and forth about that point. And this is an undamped solution, and it goes on forever, believe it or not. That's not really how wind vanes perform, and we're going to look in another video at another solution to this equation where the oscillations get smaller with time. We call that a damped solution. But we'll wait for that for another time, and we'll wrap up here.